Good evening, all. Welcome to the third webinar session on the cellular automata that we have started on 16th of August. We already had two sessions, as you may already know. First was on formal logic of cellular automata, and second was nonlinear maximal-length cellular automata, better cryptographic primitive. Today's topic is algorithmic information dynamics of cellular automata, and the talk will be delivered by Professor Hector Zenil. When I approached him, I was not sure that he will be agreeing to join us. So let me first introduce him. Professor Zenil has graduated from the University of Lille and Sorbonne in Paris with a master's and a double Ph.D. in theoretical computer science as well as in philosophy and epistemology. He did his postdoc from University of Sheffield and later was awarded a distinguished John Templeton Foundation Fellowship and grant. He has worked as a senior research and faculty member at the prestigious Department of Computer Science in the University of Oxford. He is the founder and director of Oxford Immune Algorithmics Lab and co-leads the Algorithmic Dynamics Lab at the Karolinska Institute. He is also the managing editor of Complex Systems, the journal founded by Wolfram, and member of the editorial boards of several journals and book series. He led and introduced the field of algorithmic information dynamics in cellular automata. Currently, he works on the foundation of symbolic computation in machine intelligence. In his own words, he is a computational natural scientist. So, hope we will have a very enlightening discussion and talk today. So, over to you, sir.
Maps a single graph or any graph at all, because actually there are some sequences that don't map to a graph. But this one was constructed precisely to map it comes from a graph, so we know it is a graph, the degree sequence. And then that theorem basically tells you that the only graph that you can build from that degree distribution sequence is exactly this one. So again, it is deterministic. And this degree sequence is basically the natural numbers. So in other words, also the Champer own number, which it is known to be Borel normal, which basically means that there's no over representations of any subsequence in the sequence. And so every 5 zeros has exactly the same frequency as any 5 other digits, any 5 2s or any 5 3s. And if you take any other subsequence, it's going to have exactly the same frequency in the full sequence. So in other words, that is exactly the definition of entropy, right? So the definition of entropy is this one. There are a few variations, but this is basically a measure that is depending on the base. It is always a real number, but it could be measured in bits or in something else. But basically, it is a measure that tells you how many times an object is repeated according to a distribution. And that's the whole point, that entropy cannot be independent of that distribution, and that you actually have to have access to that distribution to make sense of Shannon entropy. And that is the whole point in science. Usually we don't have access to that distribution, so we have to make assumptions. And as soon as you make the assumption of a uniform distribution, what Shannon entropy is actually measuring is just a counting function. It is telling you how many times something is repeated in that distribution. So it is a very simple function when you don't have access to the distribution, and Shannon entropy itself doesn't give you any methods or tools to actually access that probability distribution. So obviously the question is what kind of methods or tools we could use to actually access that distribution, or whether there could be a measure that is independent of that distribution. And we will see that actually that is the case. So again, coming back to this, we have the degree sequence. So the degree sequence, for those that are not familiar with graph theory, it is something very simple, and I'm sure pretty much everyone here knows what is it. So it's basically just a sequence of the degrees of each node, and obviously you can take any order, or it doesn't matter what order you take. It is exactly the same, because basically it will be a random order. For an obvious one is just to take 1, 2, 3, 4, 5, which is exactly the distribution of this one. There are some remaining nodes that actually don't follow that sequence, but we also show that those ones are vanishing towards density 0. So most of the sequence basically looks like the natural numbers. And that's what actually we wanted to show, because this means that if you look at this graph from the perspective of the degree distribution, then channel entropy is going to tell you that it is random, that it is a typical random graph. And we know that it is not, because actually I just told you the algorithm, and it looks like a very specific and kind of well thought object. So it shouldn't be classified as random. Now, if you are interested in how the distribution of the degree sequence digits look like, then it's fine to think that perhaps channel entropy can tell you something. In this case, it would tell you that the chamfer own number is Borel normal. But if you are thinking in other terms of randomness, intuitively, what you are talking about when you are talking about randomness is unpredictability, uncompressibility, those kind of things. It is beyond just a statistical description of the object. Now, let's look at how the adjacency matrix looks like, which is another way to describe exactly the same graph, right? And we also know that from the adjacency matrix, we can reconstruct exactly the same graph, in this case, even labeled, because obviously the rows and columns have labels. And what happens is actually that the adjacency matrix looks like this when it is growing, when the graph is growing. And then we have here the continuation. So basically it's a band, a stripe or something like that, coming in diagonal, and that makes sense, obviously. But basically what we've shown, and it is very intuitive, is that this is a very sparse matrix, and gets sparser and sparser, meaning that basically this is a matrix full of zeros with only a kind of with a triangle or cloud in the middle with ones. What does that mean? That basically the entropy is very low, right? Because you have all this concentration of ones in the middle, and everything else is zero, and the matrix is growing exponentially, right? Because it is a square. So on the one side, entropy is telling you that if you look at the degree sequence, this is a maximal entropy object, so maximal randomness. And if you look at the adjacency matrix, it is telling you that the entropy of this object is going to zero, so minimal entropy, highest order. So which one is right? Both of them are descriptions of exactly the same object. And that is the whole point of this graph, because it is telling you basically that the measure, and this is not optimal, obviously, right? Is dependent of your description, especially if you're measuring randomness. So I told you the algorithm to construct this network, and this is basically the algorithm written in Wolfram language, or Mathematica. And you can see that it is very short. It is short because actually it reproduces any number of nodes of the graph and remains the same size. So the only thing that is changing is basically this n, so how many iterations of this. So the whole computer code only grows by, I think it's a logarithm or double logarithm of n, right? Because this is only growing very small compared to the whole code and compared to the graph that is growing very fast. So we would like to capture this because this is independent of the language, right? It doesn't matter if you come up with another computer code. In principle, I mean, unless you are used to infinite programs that nobody really writes, you will always come up with a finite fixed size computer program. And this is very relevant. And this is exactly what we would like to capture in a measure that is independent of language. And that measure already exists. So actually was introduced in the 60s. And it is called Kolmogorov complexity, but it can be also called Kolmogorov-Chaitin, or some others call it also algorithmic complexity to be more neutral. And this measure has many advantages and also has some disadvantages. So actually, when I introduce some of the measures that we have come up with, you are going to see that actually what we did was to combine both of them to basically get the best of both of them. So here are two other examples with sequences. So some of you may be familiar with the tumor sequence, which is algorithmically produced. So you start with a 0, and then you binary negate the 0, and the following digit is 1. So now the new sequence is 0, 1, and you negate those two again. So the negation is 1, 0, and your new string is now 4 digits. And then you negate those 4 digits again, and then you have now 8 bit digits, and so on. So it is very, very easy to construct. This obviously grows exponentially, and it is recursive. But again, it was proven to be Borel normal, which again means that it is statistically random. It is maximum entropy. But it is not what you would like to say about this sequence. No? Among all possible random sequences, if you find this one, it is not the kind of characterization you want to do about this sequence. You would like to say something more that is actually produced by a clever algorithm. The same case with pi in binary. So this looks pretty much random, although there are some ones here and zeros together. But even when there's no Borel normal proof of pi in any base, all statistical evidence suggests that it is actually the case. So this is also maximal entropy. And again, if you are shown this sequence, you wouldn't like to have pi characterized as something random. Perhaps you can say it is random looking, and for those kind of things, it is very useful Shannon entropy because it gives you the statistical distribution of the digits. But it tells you nothing about the generative mechanism, which is what we are interested in science, right? We want to find the models, the cause for that sequence. And this is at the heart of Kolmogorov complexity or algorithmic complexity. So the definition tells you that the measure K, Kolmogorov complexity, is basically the length of the shortest computer program P that running on a universal Turing machine produces a sequence. So there's a generating mechanism, both P and then U, which is the one that is running the program. And this is basically what gave rise to what we call algorithmic information dynamics, because it is trying to connect this highly theoretical definition back to science, basically. Because actually we are not much interested in the minimum program. In science, what we want to find are models that are able to explain S. So the minimum program is very useful because you don't want those kind of computer programs that are basically just printing the object itself. So print S, that would be like cheating, right? Because print S is basically the same size as S, if not a little bit more because of the print instruction. And in science, that's not what we like to do. We don't see a natural phenomenon, and then we say, oh, actually, this is what can explain it, and then the description is basically the same size of the phenomenon or even larger. That is not a useful model in science. So that is the only purpose of minimum. But in science, basically, what we want to do is basically to find shorter models than the phenomenon itself. And then we would have models that can explain some phenomenon, in this case, for example, S. So this is not any measure, by the way. So it came up in the 60s, and then many people also try to characterize a randomness in many ways, from the perspective of unpredictability, uncompressibility, and typicality, which is some sort of a combination of algorithms and statistics that we're not going to talk about, but you can look it up. And basically, all these independent measures were found to be strongly and deeply equivalent when it comes to the constructive version of the measure. And that basically means that we are talking about a very fundamental measure. It is not just another pet measure of complexity. And this is actually the mathematical definition of randomness in the last 60 years, and nobody has challenged it. So if there is anything settled, it's actually the definition of randomness in mathematics. So it comes as a surprise that in science, we are still using statistical randomness for pretty much everything. And entropy is kind of a trendy topic these days when it was introduced in the, basically at the beginning of the last century. And in its informational shape in the 40s by Shannon. So this measure is also an old one, but not as old as entropy, which is literally steam engine physics. No? And I know I don't want to be despective, but basically we are using tools that have been around for a long time. And it has been our view that actually we can make progress by trying to look to more mature definitions of concepts like randomness. So one problem obviously is that not everything is nice and easy. So this measure was proven almost at the same time to be uncomputable. But to be fair, we have to say that it is lower semi-computable, which is a completely different thing, right? So lower semi-computable is something similar to what we always do in science, which is to come up with approximations of something. I mean, when Newton came up with the gravitational laws, nobody said that it was actually the last model of gravitation, and actually science is exactly that. It is a mechanism to update your models all the time. So that something is approximable only, it doesn't necessarily mean a bad thing. It basically means that it is up to standard to be able to deal with the complexity in science, and not to settle in something that is so simple as a statistical measure. So lower semi-computable means that basically you can approximate this measure from above. So you can give bounds on the complexity of an object. And that is very good. It is computationally expensive, and methodologically is more difficult than Shannon entropy. But these days we put so much attention in data that I think we should put also more attention in the methods used to analyze that data. So another kind of negative reading, which actually it was a positive reading when the theory was founded, is what is called the invariance theorem, which is exactly what measures like Shannon entropy don't have. So this is the independence of the language or the description of your object. So what the invariance theorem tells you is basically that if you measure the algorithmic complexity of an object using two different descriptions, for example, using two different reference universal Turing machines, U1 or U2, then the difference is going to be bounded by a constant that only depends on those two the models and not of the object itself. And that is very good because it basically means that this measure makes sense, because it is not dependent on an arbitrary choice of description language. And this makes a lot of intuitive sense as well, because you can think of C as the length of the compiler that basically sends you any computer program from one programming language to the other one and back. And that's precisely why you need a universal computation, right? Because you want to guarantee that actually you can write and translate any program from one to the other. So this is a positive result, but actually in practical terms, it is also a negative one, because it doesn't tell you the rate of convergence, right? So it tells you that it is bounded, but this C could be huge. And actually the behavior at the beginning could be anything, right? This would be the ideal case, that when you take longer and longer sequences, basically the C becomes more irrelevant, and both of them basically converge, both measures. But the invariance theorems is basically telling you, oh, maybe at the beginning it actually grows and comes down again and grows. And the invariance theorem only tells you that at some point in the limit, these two things are going to be convergent, but nothing tells you what happens at the beginning. But still, you can do all sorts of things, and actually even tested this statistically, because just as with incompleteness, for example, we don't find it so much when in the practice of mathematics. It could be also the case that for most choices of Turing machines, this kind of behavior never happens. And actually, in one of our papers, we've shown that not only for Turing machines, but if you change completely the computational model, most of the behaviors, if not all of them, look like this. And this basically means that if you are not on purpose designing a computer that is trying to introduce this kind of abnormal behavior, then most of the natural models are going to behave like this. So having said that, some people have been testing or using algorithmic complexity in many fields, but they usually do it by using statistical measures like popular lossless compression algorithms. So most people think that lossless compression algorithms are related to algorithmic complexity, and that is completely true. That is the whole point. Or implementations of popular lossless compression algorithms are completely based on statistical measures, in particular channel entropy. So these measures are kind of black boxes that only because we don't fully understand how they work once they are applied, that doesn't mean that actually they are connected to the measure that we originally wanted to be connected with. So if you open the box of the Lempel-Sieve compression algorithm, for example, there's nothing there that is capable of characterizing algorithmic signals in the sense of, for example, coming up with an indication that the sequence of natural numbers actually come from the successor function, for example. There's absolutely nothing, no capability in those kind of popular lossless compression algorithms that would bring that capability. On the contrary, what you have actually is that these compression algorithms, what they do is to basically count the number of repetitions of a statistical regularity in a string or in a file. And that is exactly the definition of Shannon entropy. So in some way, we have been fooling ourselves, believing that using compression algorithms has anything to do with algorithmic information theory or algorithmic complexity, beyond the obvious connection between Shannon entropy and algorithmic complexity, right? Because if something is high algorithmic complex, then it has to be high entropy. Otherwise, it would have statistical regularities that you can take advantage from and have a low algorithmic complexity. But what doesn't apply is the other way around, right? So high entropy doesn't mean high algorithmic complexity, yes, as we just saw with the description of the graph or the strings that I showed you, the tumors and the pi. So there's some obvious connections between Shannon entropy and algorithmic complexity, but those ones are trivial because they've been known for a few decades and there's nothing more to tell about them. So when we tell that we are using algorithmic complexity, what usually we should be meaning is that we are going beyond Shannon entropy. But by using something like a popular lossless compression algorithm like LC or LCW, we are basically fooling ourselves. And this is an example of a paper by Cilibrasi and Vitani, which, by the way, back then I think it had some purpose and did some good for the field. Because basically what it's telling is, okay, if you use a lossless compression algorithm, you can come up with something that makes sense and conforms to the expectation of the theory, even if that theory is mostly Shannon entropy, not really algorithmic complexity. So what this paper did was to apply compression to full genomes and then look at the compression ratio. And what they found is that basically they could reconstruct a phylogenetic tree that would relate every two species known to be related to each other by just looking at the compression rate. And well, if you don't know much about the algorithm and also not much about biology, this looks pretty much surprising, and it's pretty cool. But then, as I said, the black box, you cannot expect the black box to do something that is not designed to do. And on the other hand, if you know biology, you know there is something called GC content. And GC content is basically how many times the nucleotide G and nucleotide C appears in basically the 4 nucleotides in the genome. And this is a well-known fact for decades that basically two species that are related to each other only because of evolution, basically they would have about the same number of distribution of nucleotides. So this is almost like an evening project of counting G's and C's in genomes, and there's absolutely no need to apply lossless compression or even Shannon entropy. And there was no control experiments in this paper showing, for example, applying a compression algorithm would give something additional to what we already know in biology. Nevertheless, these two people actually came up with a book that popularized the field, but unfortunately they have been using lossless compression algorithms, and they just did it actually a few months ago for COVID-19, and that is quite, I think, can be seen a little bit opportunistic, especially in the face of the criticism that we have made on these kind of approaches. And there's all sorts of people doing this. This is actually a paper published in Science, so this is even more surprising. And they are proposing a measure of consciousness, or in the middle of the paper, they basically switch to claim that they are going to relate it to algorithmic complexity, and the way they do it is actually using, again, LZW, which is this popular lossless compression algorithm. There was absolutely no justification to make the connection, but let alone that, as I'm saying, lossless compression algorithms like LZW don't give you anything beyond Shannon entropy. So the question is, can we do better than that? No? Obviously, because it is very easy to come up with a criticism about it, but maybe that was the best we could do. No? But actually, we think we can do better, and we proposed this more than 10 years ago, maybe 15. And this is based on a very beautiful idea that is called algorithmic probability by Solomonov, Levin, and Chaitin, also in the 60s. So actually, algorithmic probability is equivalent to algorithmic complexity, and we're going to see how. So the idea goes as follows. Imagine, you may remember this whimsical infinite monkey theorem, which is basically a monkey, which is a source of randomness, randomly typing on a typewriter. And if you do the math, you can see that just by chance, a monkey can produce the works of Shakespeare. Or if you actually do the math, then it turns out that it would take several times longer than the age of the universe. But the point is that if you wait long enough, you would get it. So obviously we haven't waited long enough, and we have the works of Shakespeare shorter than the age of the universe. So how that happens? So the idea is actually that what happens if you replace the typewriter by a computer? So now instead of typing randomly keystrokes, now every keystroke is actually an instruction to a computer program. So basically the monkey is now typing computer programs. Again, these are random computer programs, so they are computer programs. So in the sense that at some point they are going to hit, for example, the enter key, and it will run something. So that is very interesting because things change dramatically. And this is basically one way to say that the world, for example, doesn't work like a typewriter. Because in the world, there are like physical laws that actually shortcut many of the things that we do. But independent of that, so let's say that we just replace the typewriter with a computer. Now let's think of an structured object like pi that we were talking about before. So if you wanted to produce all the digits of pi by randomly typing on a typewriter, you wouldn't ever get it, no? Because it is infinite. But let's say that you want to get the first 1,000 digits. Then the probability of getting it right vanishes exponentially, right? Because maybe you get the first digit 3 right, and then the second one 1. It's more difficult that it follows the 3, right? So it is 1 over the number of digits that you want. No, actually 1 over the base of the pi to the power of the number of digits that you want to get right. So the probability vanishes exponentially. But if you change the typewriter by a computer, then what you have to do is to come up with a computer program that produces pi. And pi, because it is a low algorithmic complexity object, which means that has a short description, a short formula, or a short computer code, then it means that the classical probability is much higher than trying to come up with a program that actually produces something random, right? Because pi has a short description. So just by chance, the monkey would have greater chances to type the program that produces pi. So things change dramatically because the classical probability of getting pi right is very large, if not infinite. But the algorithmic probability of typing pi by using a computer program is incredibly um, um, greater. So much more chances to produce pi if you use a computer program than by typing the digits. And that is called algorithmic probability. And you can see the connection to algorithmic complexity, because if you want to produce a computer program that produces an object of low algorithmic complexity like pi, then you have a high classical probability to actually make that happen. And this is just what I said. So something that is not complex has high probability to be produced, like pi. And something that is very complex then has a low probability to be typed at random. And these are the definitions. This is the definition of algorithmic probability. Basically, I gave you the classical probability of getting pi right? It was 1 over the base to the power of the many digits. But now it is not. Imagine that pi is in binary. Now it is not the number of digits that you want to get right, but actually the number of digits that the shortest computer program has in order to produce pi. And because this is much shorter, then the algorithmic probability is much greater than the classical probability to produce pi. And this is the formal connection to algorithmic complexity. So basically it's an inverse connection. So the higher the algorithmic probability, the lower the complexity, and the other way around. So we can exploit these kind of things to actually come up with something more powerful than a lossless compression algorithm. And what we did was this, and this explains what we did. So you run an enumeration of Turing machines. It could be anything else, again, because of the theory robustness to change of description model. And then what we do is basically to count how many times a string is produced by a large set of small computer programs. So basically, we come up with what is called the universal distribution, which is basically the distribution that you get from algorithmic probability. And then once you have that universal distribution, you can apply it to anything else. Obviously, there's a lot of technicalities here because one of them is uncomputability. So how do you know that your computer program is going to halt? But you can always do very good guesses. And this is actually why this is semi-computable, right? Because you can still approximate it by by cutting the runtime short, basically. We did all sorts of validations, by the way, because once we find the shortest computer program going from computer programs that have 0 length to larger length, you will know which is the shortest computer program that produces a string. And then you can compare that length of a computer program with how many number of times you found a program that produced that string. So basically, kind of the traditional definition of algorithmic complexity in this space of Turing machines versus the universal distribution that comes from this small Turing machine space, and then you compare both of them, and if they coincide, it basically means that it is conforming to the theoretical expectation, and that was the case. And there's no reason why they would have coincide, so it's not that we are fooling ourselves. And then you can do this by changing also the computational model and get everything right. So coming back to science, now we have a way to actually come up with generative models. So we have an observation, let's say that is this one, and then you want to say something interesting about them. So because we run already a lot of small computer programs and we have a distribution, a universal distribution, we can then know actually and find the small computer program that can explain this sequence. And actually this is one, for example, but this is a binary representation of this decimal sequence. But you can see the difference, right? You were using channel entropy. Again, this would tell you that this is a highest randomness, but when you are using our own algorithms based on algorithmic complexity, you would find the computer program that produces this string. And basically because this is small, this is fixed size, and not only that, but you know that not only it is low randomness, but you can come back to the actual computer model and perhaps even a set of computer models able to explain this, and then do analysis on the generative model. So this is all what science is about. So instead of staying at the level of statistics and correlation that channel entropy would suggest, you actually can come back and analyze the model that is explaining your piece of information. So again, we did all sorts of tests to see if we were doing something different to lossless compression and channel entropy. Actually, we do. So if you plot the distribution of entropy and compression length on a sample of strings with 100 digits sorted by density of number of ones. So basically here we have the strings with all zeros, and here the strings with all ones, and that's why it has lowest entropy and highest compression rate. So it is the inverse of compression, this one. You would have them at 0, right? Because a bunch of zeros and a bunch of ones are highly compressible and also low entropy. But the interesting things are what happens here in the middle, right? So basically, compression and entropy distribute these values in a Bernoulli distribution. But then you are seeing that our method based on algorithmic complexity has a different shape. So this is approximately actually a long tail and an exponential distribution if these gaps keep increasing. And this is a trend actually. So you can increase the string length and you would see this one growing. And this is what we call the causal gaps, because it's basically telling you, oh, actually entropy or Shannon entropy or compression is telling you that some objects are more random than they actually are, because we were able to find a small computer program that can explain it. Actually, here are two examples. So these two strings look random and difficult to compress, but they turn out to have small computer programs that can explain them. So this is not only relevant to universal computer systems, we also made these findings by restricting the computational power. So we explored the Chomsky hierarchy, and we found that up to 60% of the simplicity bias in the distribution of running random computer programs in each of these computer models could be explained by the bias introduced by algorithmic probability. So that is very relevant, but because some people would tell, oh, we cannot apply this to DNA because you are talking about universal Turing machines and nothing is telling you that biology implements Turing machines. It is almost irrelevant. I mean, almost any of these computer models that you would apply actually would reproduce something very similar to the phenomenon predicted by algorithmic probability. So how does this work in the real world? And we are getting closer to cellular automata. So in the real world, let's say we have something like this, which it is a sequence of events that are connected causally. And what we do is to basically sample some of the pieces, the observations, and obviously describe them in some code. We will see some examples. And then we try to find out whether we can explain patches of those observations with small computer programs, because obviously we don't have the large computer program that would be able to explain the whole scene, right? So what we have to do is actually to look at small windows and then decide whether some of these events could have been explained by a generative mechanism. And when I say a program, it is not actually a program, but many programs explaining this one. So if you have a bunch of small computer programs able to explain something versus perhaps no program smaller than the observation itself, it is informative of what could be going on in that scene. And actually what we do is to traverse a piece of information like this. So we traverse it all the way, and there's some overlapping. Actually, we have a full paper only talking about what happens with the overlapping, because it is actually quite technically difficult to deal with, because then you overestimate or underestimate the complexity or randomness of the object. So you have to be aware of that and then make corrections. But then it comes algorithmic information dynamics. So everything I talked about before is basically what are the methods that allow algorithmic information dynamics to actually come into being, because we needed actually these methods to be able to support this new framework. So this framework is about making perturbations to data or interventions to objects, like a file or a string, like the ones that you have on your screen. And obviously, normally perturbations are very small, so we needed something that is sensitive enough. And if you use something like lossless compression, if you compress this string versus this one, the resulting file is going to be the same size, and you can do that experiment. So basically, compression algorithms just collapse all cases into a few ones, and there's some ideas of how that happens, because there are checksums and those kind of things. And again, because this is not compression algorithms are not equipped to do anything algorithmic. It is mostly statistical implementations. So we have an original string and we do a perturbation. And what algorithmic information dynamics tells you is that basically now with the methods I was talking about, you can look at the size of the generative models explaining both the original string and the string after the perturbation. And basically that tells you something about the perturbation and the object itself. So obviously if the string is highly patterned, so it is both low Shannon entropy and also low algorithmic complexity, just in this example. And then if you destroy that pattern, then obviously the explanation or the computer program that is able to explain that digit change is going to increase the size of the original program, because the original program was just repeat n times 1 0, right? That was the computer program to reproduce this string. If you introduce a random perturbation, and actually this is not completely random, so we flipped one to destroy the pattern. Now the original computer program that was about repeating 1 0 n times would need to account for the perturbation. So the new observation would have higher algorithmic complexity than the old one. But this doesn't happen all the time. So if this were random, then our random perturbations wouldn't give you any difference. And this is exactly what I was telling about. So if the original object was random itself, then the computer program that is able to reproduce that object is already of a large length. And if you perform some perturbation, then you end up with a computer program that has pretty much the same length. So performing perturbations of data doesn't only tell you something about the perturbation, but the data itself. And then you can apply the same idea to graphs. And that is what we did. So with graphs, we have done a lot, and it is incredibly interesting. So with graphs, you have again an example, for example, of a simple graph, which could be a complete graph of any size. And basically, the computer program tells connect every node to every other node. And that is pretty much the description of any complete graph. But then you have a random graph. In a random graph, you have to specify the endpoints of every edge. So basically, the computer program grows at about the same rate of the Erdős-Renyi random graph. And then you have complex graphs, which basically are like in the middle. So in the middle of these two extremes. And then you have also a computer program that is in the middle of these two extremes. And algorithmic information dynamics basically tells you how the new description should grow against the original description of that object. So for graphs and two-dimensional objects, for example, we use two-dimensional Turing machines. And we could use also cellular automata because they are two-dimensional objects. So basically the question is, how algorithmic probable is the adjacency matrix behind a graph? And you can see, for example, with two-dimensional Turing machine that are also called termites, the question is precisely that. So how probable is that a random Turing machine produces this exact pattern supporting this graph? So there are all sorts of interesting questions, because obviously you may know that if your graph is unlabeled, then it has many representations, right? Not only one agency matrix, but all of these ones. But what we have shown both theoretically and numerically is actually that any of these matrices would be a good representation of the automorphism group. So obviously in practical terms, there could be some that have lower algorithmic complexity at the beginning, but they all converge to the same value. And we came up with a definition of algorithmic complexity on the automorphism group. And now there are several groups working on this after our own definition, working on all types of graphs and networks. So algorithmic information dynamics again applies to graphs, because then now you can perform perturbations to nodes or edges, and then see what is the contribution of each of these elements to the overall object. And you can have something like an information spectra, basically grouping those colors. So for example, in a random graph, all the nodes could be blue, right? In the sense that if you remove anything, basically the description remains the same. So the information spectra will be all blue, for example, and so on. So this is a very nice way to actually analyze both the parts and the connections of a graph in terms of algorithmic complexity and randomness. And we have shown, by the way, all sorts of interesting things apply to science, both to DNA sequences and genetic regulatory networks, for example. So this is a summary of what we do with all these methods. So basically what we are doing is to mine the Platonic space of computer programs. So I call it Platonic because you cannot actually fully explore any of these spaces, because you will always face uncomputability. So this is like an open boundary cube. Then you have algorithmic information dynamics, basically giving you some guides on how to explore that space, and maps the computer programs that you find in this Platonic space to your actual object. So it tells you, because we never find the computer program explaining the whole thing, because you would need perhaps longer than the age of the universe to find all the models explaining any possible piece of data. What we do is to cut it into small pieces. No? So every one of these chunks is telling you, oh, actually this chunk is associated to a large computer program versus, for example, this other chunk that is a small computer program. Usually you don't see this kind of diverse mapping. So if you have a low complexity object, you see all of it in blue. But this could be also the case, especially if you are doing perturbations. Random perturbations basically means that you couldn't account for these perturbations in your original data. And then you can map this one into some sort of landscape, where we have done interesting things related to reprogrammability. Because now the question is, what would it take for these small pieces that are suggesting that are random perturbations to come back to the original description, the low algorithmic complexity description. So there's a process of reprogramming some parts of the object into a low complexity state. And that basically gives you a reprogrammability landscape. So when it comes to cellular automata, this is a work in progress, and actually a new paper is about to come in Eric Gould's anniversary book. And but this is actually something that we already published in one of these papers, iScience. And this is about reconstructing space-time diagrams by algorithmic information dynamics. So we have the original CAs, so this is the ground truth. And then you scramble the rows, and that is what happens in science. So you are seeing some unfolding phenomenon, but you don't really know what is the generative mechanism, and perhaps the observations come at random. And then the question in science is, okay, we want to reconstruct what was behind. And this is a reconstructed model. So obviously we are not showing the scrambling rows because it would look just random. So that one you can imagine. But after scrambling the rows, we apply the minimal K algorithmic complexity configuration, and this is a reconstruction. And you can see that for simple objects, it is very easy to reconstruct them. And for some of them, it is not that obvious, but actually it comes with a very good model. So this is actually, again, what happens in science. And all this is about connecting back to science, because complexity science has done a lot, but I think it is now a good time to actually connect to science. So this is a model trying to explain this piece of data, and it doesn't look like completely insane. It has some elements, perhaps in inverse order or something, of the original piece of data. The same, there was one. So actually, we took also the Pearson correlation, and in most cases, it has a very good correlation. In some others, it is not that obvious, but if you see the actual model, you see that it resembles visually, and this tells you also again why correlation is not a very good measure. So this is pretty cool. And actually, for example, in this one, we came up with exactly the same reconstruction, but this one has also the same value. So I didn't want to fool people and actually picked the one that doesn't look exactly the same. But this is even more interesting because these are like snapshots. So we reconstructed the thing, but we don't know what came before what. But this one now it is reconstructing the dynamical system and indexing every one of these rows. And now this is why you are seeing that there's some errors here. So it has the trend, but actually it is not perfect. And we know why. It has to do with the boundaries. So actually this can be corrected because we know that, for example, we are taking chunks of size 4 by 4, then every non-4 multiple, we are going to have an error that we can correct. So again, I didn't want to correct this. So this is the raw method, reconstructing the cellular automata. And you can see that, again, there's a good representation, even in this one, because, I mean, compared to something random, this is still a very good model of what the original thing could have happened. Because again, this is not just a reconstruction. We have the computer program that reproduces this representation. So even for difficult ones like these ones that are more random looking, you can see that the p-value is high, and not even looking at the p-value, but the qualitative features are close to each other. So with rule 30, for example, it's interesting. It was almost like reversed. So I'm going to stop there. There's a lot of more stuff that we can talk about, and I have some time to answer some questions. But this book is coming soon, published by Cambridge University Press, hopefully this year. But we have been saying the same for the last 2 years. So at some point, I'm hoping it's going to be published. Thank you very much.
Thank you so much, sir. It was an exciting talk, and we are just, I don't know how to express it. So I am expecting some questions from some of our audience. Who is going to be the first? Anyone having any question?
So I have one question actually. So thank you, Professor Zenil, for the nice talk. So it is, so enlightening. So thank you very much. So I have one question. So regarding, you're talking about, randomness many times. So, I mean, how can we use this algorithmic information theory to measure the quality of some random number generator? So, some pseudo random number generators are there, and who's supposed to produce the random numbers, and sometimes their quality matters, So how this theory can be applied to measure the quality?
Yes, absolutely. So it can apply. It can be a new battery test for a random number generator. So for example, we apply these measures to pi itself, because I've been putting pi as an example. And now it was the time to actually test it. And it is a very difficult thing to do. And actually, we kind of pick up the signal, and for longer sequences of pi, we see a trend of lower algorithmic complexity. It is still quite high, because we are not saying that we are solving everything. So actually, these are very difficult problems. And if we had picked up that pi was actually pi, we would have probably solved the science. No? But here it's all about trends. And what we were able to see is actually that pi doesn't have highest algorithmic complexity using our own methods. And that is very interesting because it does have highest Shannon entropy. So any indication of that it is not the really highest entropy would be still useful. And that is actually what happens with our measures. Another interesting application is if in chaotic systems, because chaotic systems may also look random, but actually they are completely deterministic. So it's kind of similar situation. And this is exactly the kind of measures you would like to have to characterize chaotic systems, not to characterize them just as a random system.
So any battery, have you developed any battery already available? No.
Yeah, many. So a lot of people have contributed to libraries, and in R, for example, the computer language R, it is now part of the standard library. So you can just type, it is called ACSS, I think, the library, and it gets downloaded and ready to be used. We also have a online complexity calculator, so you can do several things online, but for short objects. But there are also libraries in C, and the most developed one is in Python. So for Python, there's a couple of libraries that you can download from our website that will be ready to be used.
Oh, thank you. Thank you very much. I have one more question. It's my brief question. So when you are talking about infinite monkey theorem, then one point was there that computer better than typewriter. So that point I didn't understand. So you made a comment, from the infinite monkey theorem, that if a computer is sometimes in some sense better. So why it is so?
That having a computer is better than a typewriter?
No, so from randomness point of view, does it have any advantage you have?
You mean by having the monkey or the computer?
The computer typewriter.
Yes. So it is not about whether it is better or not, but how it changes the relationship when it comes to asking what is the probability of an object to come into being. And this can even get connected back to creationist claims, for example, right? Because some people say, okay, how by random mutations in evolution we can see such complex animals, right? Because you cannot reproduce this in a computer simulation just by making random mutations. And the difference is that we are not running in a random world. It is a world with laws that are almost like computer programs. So all these biochemical reactions, for example, behave more like computer programs than random mutations. And that basically is a speed up. So actually we have a paper on this also as well. And we show how we can speed up even evolutionary programs by introducing algorithmic probability. So basically biasing towards simplicity or structure. And that gives you a speed up. So it is all about studying what happens by changing the typewriter rather than saying that it is better to have a computer, which I would say it is better because you can get to structured objects faster.
Thank you.
Thank you.
Okay, any more questions?
I have a question, please.
Please.
Hi, Genaro. Good to see
Hello,
you.
Hector. Nice to meet you. How do you think about how random is it find truth or complex function across of these entropies?
Could you repeat it again because it was breaking up, Genaro?
How frequently is to find a complex function, complex behavior in the universe across of entropy?
That's a great question, Genaro. So it depends on that is one of the cases in which actually the description language changes how often you get a complex function. So if you are using Turing machines, for example, Turing machines are quite boring. And now I can see why Stephen Wolfram was using cellular automata. Because it takes thousands of Turing machines before you actually see something interesting. But as we know, for example, looking at the elementary cellular automata, you can immediately find a few very interesting cases, especially for non-simple initial conditions. So what is interesting is what the theory tells you is that at the end you are going to have the same distribution in principle. But again, this is related to the invariance theorem. How fast you are going to see them, it is very different. And this is key also because we have tested this with the Encyclopedia of Integrated Sequences. You remember this online repository, where mathematicians submit their favorite sequence. And it turns out that they don't submit any sequence. They submit those ones that are more interesting. And when you look at them, the distribution against the universal distribution, there's what we call a social gap, basically. And it turns out that we are more interested in sequences of that type. No? So we think that pi and primes are very interesting because they have this structure. But they are less interesting when you just run all computer programs. So what we were also trying to do is to quantify in what computer programs you could get recursive sequences faster. And it turns out that, for example, in Haskell, you could reduce in 2 orders of magnitude how fast you can produce recurrent sequences.
Very interesting. Thank you, Hector.
Thank you, Genaro.
Bye.
Okay, any more questions? We can take 1 or 2 questions.
Great. Well, I want to thank you again, Kamalika, for the invitation.
I am very much thankful to you for the nice talk. It was really enlightening. And some of the things are really difficult for me to understand, but still, it was a nice thing, a nice domain to look about. Thank you so much, sir. Hope to see you again.
Absolutely. Have a nice day, rest of the day. It's very late there.
Thank you very much.
Thank you,
Thank
everyone,
you.
for joining.
Goodbye.
Goodbye.
Thank you.